Hey everyone. So in this video, we're going to understand how a layer in a typical multi-layer perceptron neural network works. And so in the previous video, right, which is part two of this series, we have understood how a single neuron works. And we've chosen the tan-each neuron, which is what our layers are going to be built out of. And now what we're going to do is build on that and assemble a couple of neurons or more and see how a layer, which is an assembly of neurons, works, right? And this is for a typical, what is called a multi-layer perceptron architecture. But that should give you a really good idea of how layers in neural networks work. So let's start with the single neuron, of course, right? Let's just say there's this one neuron. It's a tan-each neuron. Now we've seen this in a fair bit of detail in the previous video. So you have, let's say, two inputs coming in. Now this could be, the first layer in the network. And so they could be actually the inputs to the network, or they could be inputs passed in from the previous layer. So outputs of the previous layer, which are now inputs. So because we're just looking at this layer, I'm going to say X1 and X2, which are inputs to this layer. So they both pass to the first neuron. It's a tan-each neuron. And so the typical WIXI plus B. Now I'm using this one here to indicate that it's the first neuron in that layer, right? And B1 is the same. And I indicates which input it is. So this I being 1 would indicate the first input. This I being 2 would indicate the second input. And it would be multiplied by the corresponding input value. So the weight corresponding to that input multiplied by the corresponding input, right? And A1 is the output of that unit. And so taking values of 0.2 and 0.1, we know how to compute this. Let's assign a set of weights. Let's assume these are the weights associated with that neuron. Now it's two inputs, so it's going to have two weights. 1, meaning the weight of this neuron, as I explained. This 1 indicates this neuron. And this is coming from the first input. And in this case, the weight associated with the second input for the first neuron, right? Of course, if you've seen notation used in vectorization, the matrix notation is slightly different. But in this series, we're looking at the neuron, the layers as an assembly of neurons. So that's why this notation. And then B1 indicates the bias associated with the first neuron in this layer. And again, we're just looking at one layer. So what can we do? Well, we know how this works, WIXI plus B. And so 0.1 times 0.2 plus 0.3 times 0.1 plus 0.1, right? The weights and the bias with the inputs and the tan-each of that, right? We know how this works. Now what happens? Well, let's add a second neuron. And now we have two neurons, so it's becoming a layer, right? With one neuron also, you could call it a layer, but it's basically a single neuron. Now we've got two neurons. Now what happens? Both the inputs from here, right, come into this neuron. And what type of neuron is this? It's a tan-each neuron. So in a layer, you would have the same type of neuron. You would not use, say, a ReLU here, right? It's a tan-each layer, and so both the neurons are tan-each neurons, right? Now the inputs are fed to both these neurons. So the inputs coming from here have gone into neuron 1, but now both these inputs are fed into neuron 2 as well. And because all the inputs, or each input is fed to each neuron, right? So neuron 1 gets both the inputs and neuron 2 gets both the inputs. And for now, let's just say this layer has two neurons. So it's called a fully connected layer. And the network that's built with this would be a fully connected network, right? Meaning every input in the previous output of the previous layer is passed on to every neuron in this layer, right? So it's fully connected. All the neurons in the previous layer are connected to all the neurons in the next one. Okay, so giving it the set of weights, and in this case, we're assigning 0.2, 0.2, and 0.2. We've used the same weights as what we did in the Deep Learning from Scratch series in the video building a multi-layer neural network for this particular video, right? So we have assigned those weights. Now we see that each neuron has its own set of parameters, meaning it has its own set of weights and bias. So these weights and bias in neuron 1 are different from the weights, or at least are independent of the weights and bias in neuron 2. They could end up being the same when you train this, but they're independent. They're not related to each other. They're its own set of weights. So we have its own set of weights. We're assigning them to be 0.2, 0.2, and 0.2. And now it's a tan-each neuron, so you know how to compute this and you get the output, right? And so for this layer now, it's taken in the inputs 0.2 and 0.1. You can think of it as a vector, right? Two-dimensional, 0.2 and 0.1. Passed into this layer, and the first neuron has given us an output, and the second neuron has given us its output. And that would be the forward pass through this layer. So it would basically effectively be the forward pass through each of these neurons. And we've seen that both these neurons act independent of each other, right? So the computation through this neuron and the computation through this neuron are not dependent on each other. The parameters are independent and the computation is independent. And that applies to all the neurons in a layer. So if you have 10 neurons in that layer, if it's fully connected, all the inputs would go into each neuron, and then the neurons, are computed independent of each other, and you get the output. And so if there are two neurons in the layer, you would have two outputs from that. So the number of outputs is equal to the number of neurons in that layer. Okay. So we've done the forward pass, which means you can, get the output of that layer and collection of layers, a network, a connection of layers rather, and you get the output of the network. But now to train the network, you need to also get the backward pass. So let's say we're passed back. Now you have two outputs from this layer, the output A1 from N1 and A2 from N2. So what would you need? Well, if you think about this, you'd need the sensitivity of the loss function, right, which is passed back. Let's say this is just one layer, let's say layer I. And so this is passed back from the previous layer. And what we have is the sensitivity of the loss with respect to the output of this neuron, right? A1 associated with N1, and the output of the loss with respect to A2. And that would come to us in the form of a vector, let's say, being passed back. So this rather is the sensitivity of the loss with respect to the outputs of this layer, right? It's a layer with two outputs. What would we do, right? Where L, as I said, is the loss function. Well, you take dou L by dou A1 and pass it here. There's no point passing it to the second neuron because second neuron has nothing to do with A1, right? As we said, the neurons are independent. What we do is take dou L by dou A2 and pass it to the second neuron. And then what happens? So let's assign values 1 and 1, right? Could be different, but I'm just trying it with this. And so what happens? Well, you assign those values, dou L by dou A1. Now, the forward pass could be computed independently, so the backward pass can also be computed independently. And so what do we do? Well, we have dou L by dou A1 coming here. You do the backward pass, and we have done the backward pass through the neuron in the previous video, so I'm not going to repeat it. But as we know, what you get is the derivative of the loss with respect to the weights and its bias. And then you get the derivative of the loss with respect to the inputs. Right? And these are so this is just the neuron's parameter. So that's that with respect to the weights and the bias of this neuron. With the inputs, well, it's interesting because this set of inputs, you've got now the sensitivity of the loss with respect to the inputs from this neuron, right? But as we know, the inputs have been passed to the second neuron as well. So we have to wait for that. So if you take these values of 1 and pass it back, you'd get this set of weights and this set of sensitivities with respect to the weights and with respect to the inputs, right? Give it a shot. And now what will we do? Well, we take dou L by dou A2 now, and you'd get the loss, the sensitivity of the loss with respect to the weights and the bias of this neuron. And then what you get is the derivative of the loss with respect to X1 and X2 again, right? But now this is, the dependence coming in through the second neuron. So as we can see, we've got dou L by the weights part is straightforward, right? Each set of parameters is associated with that neuron. You've got the answer. You don't have to do anything else there. To backpropagate this further to the previous layer, you have to think, a little, because what happens, you have the sensitivity of X1 and X2 coming out from this neuron and from the second neuron. What will you do? Well, you add them up, right? You add up these sensitivities as I've done here with this symbol. So suppose for the first neuron, it was 0.098 and 0.29 sensitivity with respect to X1 and X2. The second neuron, it's 0.187 and 0.187, right? You'd add this to get the overall sensitivity. And so that you can think of now as the sensitivity of the loss with respect to X1 and X2, right? And it's the sum of this. Now, if you had 4 neurons in this layer, it would be the sum of the sensitivities that you got from all 4 neurons, right? And then you'd pass that back to the previous layer. In this, now, if it's the first layer, then this would be inputs, and that value, you don't need to pass it back, but otherwise, it needs to be passed back to the previous layer. So that was basically it, right? That was how you assemble a set of neurons, right? And do the forward and the backward pass. We'll code this up in a bit. But if you had more neurons, same principle, right? You have 3 neurons. The forward pass is basically now through each of these neurons. All the inputs would go to all the neurons as we discussed, and you'd get the values A1, A2, and A3, and then you'd get the backward pass to train. So you can think of a layer as a way where it's given an input, and in this case, now you have three neurons. So you have an input which is two-dimensional, right? You have two sets of values for the I minus one layer. Assume this is the ith layer. The output of that would now have three dimensions, right? It would be three-dimensional. So you can think of it as a transformation, right? It's taking in an input vector and then transforming it into a different vector of a different size, right? So that's what it's doing to the inputs. And this keeps happening till you get your output layer, right? So in a classification problem, let's say like the one we're going to tackle, you'd start with say an input vector which is 384 in size, but you only want to get an output of six, right? Six classes. So each layer would do its set of transformations, and at the end of it, you'd get a vector that indicates the class that the network that the input belongs to, right? Okay. Now the key part here is the number of parameters in the layer, because that is what we need to train, right? So that is a key question. Now, in this particular architecture with this, MLP, neuron, which is basically a linear layer plus the tanh activation, how many parameters are there? Well, per neuron, you have the number of weights, which is equal to the number of inputs plus a bias. And so for the layer, the number of parameters would then be the number of neurons times the number of parameters per neuron, which is basically the number of inputs coming into that neuron plus one, right, which is for the bias. Now, because each neuron in the layer is the same, it's basically a multiplication of these two. So in this case, you have three neurons. Each neuron has two inputs coming in. So 2 plus 1, two weights and a bias. 3 times 3 is 9. So this particular architecture, this particular layer would have 9 parameters that need to be trained, right? And now you can imagine much larger layers if, the latest, for example, large language models have billions or trillions of parameters. You can imagine how the layers are going to be. Okay, so what are we going to do now? Let's just code up. In the previous video, we quickly coded up the tanh neuron. Let's now create a simple, class or structure for the layer, which, will be an assembly of these neurons, right? Okay. Okay, so I've opened up the Jupyter notebooks and we've used this last time to create the first part, right? So I'm opening up the same notebook and I'll add a link to this in the description. So you can, at the end of the series, you can go and check out this notebook, right? But in the first part, in the previous video, we had already built the tanh neuron, right? So that is basically set. What we're going to do now is assemble it. Now, all we need to remember is what the neuron gives us in the forward pass, which it takes in the input X and returns the output A, and it stores, right, the output in the neuron as well. And in the backward, it takes the DLDA, which is the sensitivity of that neuron, output rather, to the loss function. It returns the sensitivity of the loss function with respect to the inputs to that neuron and with respect to the weights, right, and bias, which is the parameters. Okay, so let's now create this layer assembly. So it's going to be a simple class called layer, and again I'm just going to speed this up by copy pasting, right? And so I'm going to call it class layer, right? What does it take in? It takes in the number of inputs to that layer, right, the number of neurons in that layer, and the type of neuron. So if it's a tanh neuron, I'd say that. In this case, I've just called it neuron above, so I'm just going to say by default it's going to be neuron. Okay, now we're going to create a list of neurons. So self.neurons is basically a list of the neurons we've just created above, right? And it takes in the number of inputs, and the number of inputs, fully connected layer, so each neuron takes in the same number of inputs, right? And how many neurons in that list? Well, depends on the number of neurons you pass in, right? Okay, I'm also storing some of these numbers, right? So the number of parameters for that layer is the number of inputs plus the bias times the number of neurons. And then we're also going to store some of these values at the layer level, right, which is a bit of a duplication. So, eventually for production anyway, you'd use a vectorized network. In this case, I'd like to keep the values, so the A and the X, but also, so that would be at a layer level. So we can visualize this at a later point. And then of course the sensitivity of the loss with respect to the inputs of that layer and the sensitivity with respect to the weights, right? So I'm just initializing all of that to 0. The number of inputs, for example, is n inputs, and for the weights, I'm storing it as an array. So you would have the number of neurons as, one dimension, and the number of input plus 1, because you're going to store the sensitivity with respect to the weights and the bias. Okay, so what's the forward pass? So the forward pass, what does it do? It takes an x, which as we know is a vector. It's x1, x2, x3, which is basically all the way to xn. So depending on the number of, the size of the input vector, or if it's a hidden layer, then basically the output of the previous layer, and the x comes in. Now, as we know, each neuron takes in the value x, right? Each input is passed to all the neurons. So we loop over the neurons, and for each neuron we pass x. Now in this case, because it's an assembly of neurons, it's not a vectorized network. You see how it's going to slow down a bit because you're looping over the number of neurons, but you pass each neuron the x. And what does the neuron give you? It does the wixi plus b, passes it through the activation, and gives you the a, which you store here. So we've got this array we have defined, and it just stores the output of the ith neuron in ai, so the ith index. And that's the forward pass. So the forward pass, as always, is exceptionally simple. Now what do we need to do? Well, we have the backward pass, right? So the backward pass, again, in this case, because it's an assembly, it isn't very complicated. What does it take in? It takes in dl by dA. So dl dA is basically an L for loss, it's capital, is now again a vector, right? Why? Because it's a vector or an array that's a collection of the sensitivities with respect to each neuron. So you have dl by dA1, dl by d, like we saw in the theory part, and so on, right? What do? You loop over each neuron, but now you don't pass the entire array because the output of the neurons are independent, right? The neurons are independent. So if it's the ith neuron, you pass the corresponding dl by dA. So if it's the first neuron, you pass dl by dA0. If it's the second neuron, dl by dA1, and so on. What you get from the neuron, we've just checked that out a second ago. You get dl by dx, which means it's the sensitivity of the loss that comes out from that neuron, or the dependence through that neuron of the inputs to that layer, and of course the sensitivity with respect to the weights. Now the parameters are only associated with that neuron. So the self are dl by dw, you can just say ith neuron, and we're just going to store the weights there, right? And so for I is 1, it'll be, well, I is 0, first neuron, it's going to be stored here in 0, and this, and so on. dl by dx, however, is different. We need to add them up, right? So what we need to do is say self dl by dx, which is initialized to 0, and then you need to add the dl by dx of each neuron to that, because dl by dx, as we know, is eventually just going to be a simple vector, which is dl by dx1, dl by dx2, and so on, and it's the sum of each of these. dl by dx is passed back from each of the neurons. So we're going to do that. Now we're going to make one small change as well, which is, in this case, because we're just testing a neuron, it will not really matter, right? But in more complex networks, you could add a plus sign here and a plus sign here to sum up. But for now, we're going to leave it like this, right? Okay. So that's that. I'll add one last function, which is an update weights function. And so in the update weights function, what does that do? Well, when we want to simplify, how this works, you can just pass in the weights of the layer instead of passing it at a neuron level. And then what will it do? It will loop over the neurons, and then the first set of weights will be passed to the first neuron, the second set of weights to the second neuron, and so on. Okay, so this is good. Let's just rerun this quickly to make sure it's good. Let's run this layer. So, okay, I think that's set up. And now let's take the example we have set up above. So I'm going to say layer 1, two inputs, 2 neurons, right? And we're using the exact same weights as the example, 0.1, 0.3, and the bias is 0.1. Second neuron, 0.2, 0.2, and 0.2. Let's initialize this, and it says initializing a layer with a tanh activation function. Okay. So we'll do the forward pass. How would that work? Let's go there, and you want to see the outputs, and we've given it the inputs 0.2 and 0.1. We've done the forward. It will go in and do the forward pass for each neuron, and we get the outputs, which is what we've seen in the exercise, right? In the theory part. And so that's that simple. Now for the backward pass, what do? We first define the sensitivity with respect to the loss. Now, once we kind of get further down in the series, we'll actually have a loss function. And so this value would be passed back. But for now, as we've done in the exercise, I'm going to define this to be 1. I set this up to be 1. So let me run that. And then I'm going to call the backward. Right? Okay. And so what do you get? Well, L1 dot backward, you pass this in, and you get what the backward pass returns to you is, in this case, it doesn't return the derivative with respect to the weights, those are stored in. What it does return is the derivative of the loss with respect to the inputs, which needs to be passed back. So we've got, and I've called it dl by dy. So, right, or rather dl1 by dy, right, and then it needs to be passed back. The value is 0.284 and 0.48, which is what we've seen in the theory. And then these are the sensitivities of the weights for each of the neurons. So if you want to print them individually, we can do that as well. And I'm just going to say this. And each neuron, if you go, the values are stored there as well. That's why I'm doing that. So it's easy to visualize. So we see how, in this case, I'm just printing the dl by dx actually. And the sum of this is what you see here. You see here, right? This plus this would give you this, and this plus this would give you this. You can do the same for the dl dw's. Okay, so we've quickly implemented this layer. So we've gone from a neuron to a layer which is an assembly of neurons. So hopefully you've understood how this works, right? And then as we keep going, we'll start assembling our network. Okay, so let's go back to the slides for a bit. Okay, so we've coded up, the layer we have, and it's basically, in our case, a 10H layer, right? It's an assembly of 10H neurons, but you could use it as an assembly of other neurons as well, ReLU or something else. However, right, the last layer in our network for classification is going to be a softmax layer. And so that, the math of that is going to be slightly different. We haven't covered how a softmax function works. So in the next video, we're now going to understand how the softmax function or the softmax layer is going to work. And then after that, we can then go and assemble a full network. So see you in the next one.